Okay, so again, we've got, if I need to find this Darcy friction factor, it's going to be a function of the Reynolds number and epsilon over d. If it's laminar, constant value divided by the Reynolds number. That's any Reynolds number less than 2300. If it's turbulent, Reynolds number greater than 2300, I've got three options. Colebrook equation, I've got a Holland approximation, which gives me a really good approximation of the Colebrook equation, or there is what we often call the Moody diagram, which is just a graphical representation of the Colebrook equation. So three, if I'm dealing with turbulent flow, three main ways to try to quantify the Darcy friction factor. Right now, so a lot of times in a fluid mechanics class, when we're talking about pipe friction, there's two main types of problems that we'll encounter. One is where you're just simply asked to find the pressure loss, or maybe the head loss sometimes, or maybe they want to know what is the energy input required. They're basically asking you to find this loss term. They want you to actually quantify this guy. Okay? Now that's actually pretty easy to do as long as you can find your Reynolds number. And if you know what kind of piping you're going to use, then you know the epsilon value. At least we can go look that up in a table or in our text. So use the Reynolds number and the epsilon over d, epsilon divided by diameter value, to find your Darcy friction factor, which we've already talked about how to do that. Now, frankly, this is not super realistic in my opinion. It's not very often that you're going to have an existing, because this requires an existing piping system already in place, and you just need to quantify or figure out what's the energy loss associated with this existing piping system. What's more likely is you're going to be in a situation where you know the amount of flow rate that you need to achieve, or you need to figure out what pipe to go buy. You're actually going to have to purchase the piping needed to achieve a certain flow rate, or again, maybe you need to determine the flow rate. Maybe the piping system already exists and you need to know, if I hook up this pump to it, how much flow rate can I expect to get through it. In both cases, the problem with that is if you don't know the diameter, or you don't know the flow rate, meaning you don't know the speed. In either case, you look at the Reynolds number, right? Reynolds number being dependent on the speed and dependent on the diameter. If I don't know the diameter and or I don't know the speed, I don't know the Reynolds number, meaning if I don't know the Reynolds number, I don't know the Darcy friction factor. It requires a problem like this, which is a realistic situation. Right? If I've got a certain flow rate I need to achieve, I need to know how big a diameter of a pipe to achieve that. Or if I've got an existing piping system and I need to know what flow rate can I get with a certain pump hooked up to it. In both cases, you can't directly determine the Darcy friction factor to figure out the loss associated with it. You're going to have to guess and check. You have to guess a diameter, check and see if that diameter fits. If it doesn't, you'll get a better guess for the diameter and repeat. Same thing with the flow rate. Guess the flow rate, calculate what the flow rate should be based on that guess, and then repeat. Right. We're going to work some problems in the next few class periods on how to do that. Okay? But yeah, we're going to guess diameter and or the F value to estimate the other. All right. So I think that's a good stopping place. We're probably going to stop there, pick up next time, look at a couple of examples. I've got one example I like to look at 2 or 3 different ways, and so let's do that and we'll see where we get. But I think that's going to be a good starting place for us to pick up from next time. All right, guys, stay safe out there.